Swayam Prabha. Digital India. Educated India.
Good morning. This is lecture number 20 in our course on advanced structural analysis. We are continuing with this third module on basic matrix concepts as applied to structural analysis. This is covered in chapters 2 and 3 of this book on advanced structural analysis. You will recall in the last class we gave a big picture view. This picture really shows how you can do various transformations to finally arrive at what? What's the end result of this? You will get the element stiffness matrix of every element aligned along the global axis. Okay, so the end result of these transformations is this: Ki is equal to Ti transports K star I Ti. After this, your next job is to assemble the matrix and get the structure stiffness matrix. Okay, so that assembly is where some of you had a difficulty. So remember, we had some difficulty understanding. So let me tell you a story. Okay, there was a housewife who wanted to buy one of those gadgets, the mixer come grinder come juicer come so many other things. So she bought it online and this big packet reached her house. She was very excited because she had paid through credit card and all that, and when she opened the box, it looks beautiful. There was a brochure, but it all came like these matrices in small pieces, and she was supposed to assemble them because assembled is very big, the unassembled is very small. So for packaging purposes it came in small pieces. So she was a postgraduate student, so she thought she could easily put it all together. So she opened the manual and she spent 1 hour trying to put it all together, and it didn't work. Just like you didn't get the hang of this in the last class. So she kind of gave up, and in her frustration she left the house and went out. When she came back a few hours later, she was amazed to see that the matrix was well assembled already, and it's been connected to the socket plug, and she just put on the switch and she heard a beautiful whirring sound. So my God, how did this happen? And she looked around and she realized there was a maid servant in the house who was absolutely illiterate. She was wondering, did she fix up this wonderful gadget? And she called her and she said, did you do this? She said, she smiled hesitantly and said, yes. But you don't know how to read or write? And she replied, yes ma'am, when you don't know how to read or write, you have to use your brain. So your real challenge is, you are literate, you know how to read or write, you can look at solved examples in textbooks. If they say step 1, step 2, you know what all that means. But really putting things together on your own, you need to be a little illiterate and start using your brains. So here we have the challenge of both knowing how to read and write and also trying to fit it all together. So let us do this one more time, looking through the eyes of the maid servant. Okay, so you have 3 elements there. For each element in the last class we generated the Ti matrix. First we generated it along the local coordinates, then we transformed it and put it along the global axis, but we put some linking coordinates, right? So we've got those ready-made stiffness matrix boxes, and we just have to put it at the right place in the big matrix. The structure stiffness matrix, what is the size of that? It's 12 by 12. And we have these small 3 6 by 6 matrices, which we can again partition into 3 by 3, 3 by 3, 3 by 3, 3 by 3, and we need to put the right 3 by 3 box in the right slot. So all you have to look at is connectivity. Now let me help you. Take the first element. The first element is connected to nodes 10, 11, 12 and 1, 2, 3. So all you have to do is to pick up the appropriate boxes and put them into the slots as shown here. Does this make sense? It fills up only those 4 slots. The contribution of element 1 is only to these 4 slots, 3 by 3 slots, and it's direct contribution. You just have to shove it there. You don't have to play with it, you don't have to multiply with change sign, nothing, just put it there. Can you do it? That's all you have to do. Do it intelligently, right? Element 1 has no contribution elsewhere in that big picture, in that global. Take element 2, where do you think it will fit in? It will fit in, that's simple, the top corner, because 1, 2, 3, 4, 5, 6 element coordinates match with global structure coordinates 1, 2, so that's simple. And the last one will connect 4, 5, 6 and 7, 8, 9. Does it make sense? That's all. And in some places like 1, 2, 3, you will have 2 contributions, you just algebraically add them up because stiffnesses get added up. Does it make sense? That's all you have to do. And when you do an assignment, of course we will make it a small problem, you will get a first hand feel of how to do it yourself. Okay, so there is no way of learning this except doing it by yourself, like the maidservant did it in our little story. Finally, after you have got this matrix, and we will see that there are many other ways of getting the same matrix. There is a reduced element stiffness method, there is another method which we will study soon of getting this matrix, because this has a big advantage that you are playing with little boxes. No matrix is more than 3 by 3, and you are finally, so your storage is very elegant, economical. Only thing, you must program it well so that it goes to the right slot. There is a crude way of doing it, we will look at that for beginners, that you will be more comfortable with that, but when you do programming, when you want to make matrix solve a very large problem, you can't do that, that is too unwieldy. This further you can partition to the active coordinates. You have 8 active degrees of freedom and the restraint coordinates. Does this make sense? Okay. And the alternative is to use the what we call the displacement transformation matrix TD, which is what I want to show you next. Okay. But before that, let us say you have got the stiffness matrix, you can write relationships like this. Basically F is equal to KD at the structure level, but D itself is subdivided into active degrees of freedom which you do not know dA displacements, but you know dr displacement, right, they are usually 0. On the left hand side, the force vector FA is known to you, that is a load vector acting at the, FR is the reactions you do not know, right. So you can expand this into 2 equations, because the K matrix can be subdivided and they look like this. Does it make sense? So you need to solve the first equation, find out the unknown displacements dA, plug it into the second equation, you get the support reactions here from the global picture. Then the unknown displacements dA you should use using equations similar to your slope deflection equations and get the member level forces. Does it make sense? This is the big picture. Now that is what you get in a truss, because there are no intermediate loads, but in a beam or in a frame or even in an actual system like a chain where you have intermediate loads, you have to add the fixed end force effects, right, which you have some introduction to already. So you have to modify that equation slightly, we will look at that in detail later. Okay. Then let us go back, let us take another example. Let us take this frame which we looked at yesterday. How do you go about doing it? First you find Ti and Ki star, we have done this. What is the next step? Finding Ki by doing this transformation, which in MATLAB you can do effortlessly for each element. Then what is the next one? No, this is at the element level. Next is assembly. This is where you had difficulty, right? You assemble it to this form. and then you can solve for whatever loading you get. So mind you, up to this stage you are dealing with the property of the structure, and you say now give me the loads, I can handle it, but the computer does this in a jiffy the moment you feed in the geometry of the structure and the material properties. It's ready to handle any loading, because it's already going to work out these properties effortlessly if your programming is good. For example, in this structure you do it this way. Let's look at Ka. It will be a 2 by 2 matrix because you have only 2 active degrees of freedom, and Kar for example would look like this. But in this method you have to always keep track of the linking global coordinates which I have shown here. 1, 2 are the active degrees of freedom, and 2, 3, 4, 5 all the way to 10 are the restrained degrees of freedom, and Kra will be the transpose of Kar, and you can calculate Krr. You will never need Krr unless you have support settlements, because that's dr is usually 0. The alternative is this using a displacement transformation matrix. This is for people who are not very comfortable putting it in slots and all that. If somehow we could have a robust method where you do not have to keep track of these linking coordinates, then you have got a blind way of doing it, okay. Not suitable for programming large structures, but okay at your level, okay to do manually, and I think that's the way it is taught in most universities, but that's not how algorithms are built in software packages. So let's look at that. Remember I told you about 3 transformations. This one we finished, you've studied this, we know how to do the transformation using Ti. The second one is using the displacement transformation matrix. This is the way when you do the reduced element stiffness method, which we are going to study next, but you can use the same idea in conventional stiffness method, and in the next class we will look at flexibility method, where instead of a displacement transformation matrix you have the force transformation matrix. It will all fall into place. Now the inverse of those matrices helps you switch from the element level, the local level, to the global level, and there is a principle, you do not need to do the inverse, there is a principle called the contra gradient principle, a beautiful principle which we will look at shortly. Right, so let us look at these transformations. Look at this. Now I am talking about structure level coordinates here and element level coordinates here, right. I have combined them, so F star really means F1 star, F2 star, I can put them all together neatly. So does this make sense? And I am saying if you give me the global displacements, they are linked all in one go to the element displacements to a matrix which I call the TD matrix. The TD matrix is the displacement transformation matrix, and obviously it must satisfy compatibility. Likewise in the flexibility method there is something linking this to this, that must satisfy equilibrium, and what would be a good name for that transformation matrix? Force transformation matrix. Okay, we will study that later. For the time being we will look at the displacement transformation matrix and see how it works. So since we know that the displacement vector is really made up of dA and dr, then I can again partition my TD into TDA and TDR. Does it make sense? TDA into TDR, okay, and if you expand it, it will look like this. Do not get worried about the size of those matrices, it is just how it works out, how it falls into play. Now I can do something here. This D star is actually including all the elements in the structure. It is too messy sometimes, so I just look at one element. When I look at one element, the ith element, it will look like this, Di star, and this TD now becomes unique to that element, so it is TID, which can be partitioned as TIDA and TIDR. Does it make sense? This also you can do. It is actually all the Di stars put together that actually make up the D star, okay. Now let us take a look at an example, but before that a definition. The displacement transformation matrix TD is a unique matrix satisfying compatibility requirements for any given structure, and a typical element Di TD, TID at L star j of this matrix may be visualized as a displacement being transferred on account of a unit displacement at the jth coordinate to the local L star coordinate of the ith element in the structure with all other degrees of freedom restrained. That is quite a mouthful, but basically you get what I am trying to say. Okay, you remember when you have two subscript, the second subscript goes to the cause and the first one goes to the effect. Okay. Let us just try to understand what that means. Take this same structure, let us see what it means for the ith element. What should we do? Well, really we are trying to first arrest all the degrees of freedom. So you got the kinematic structure, all degrees of freedom arrested, then one at a time, let us say d1 equal to 1, you get a shape like that. We are trying to see the effect of this in each of the element stiffness matrices, each of the element displacement vector, that is what we are trying to see. In other words, if I apply d1 equal to 1, which elements will it affect? It will have first and second, the third will remain unaffected. If I apply d2 equal to 1, likewise something like that will happen. If I apply d3 equal to 1, that will happen. So you already have an exposure of doing this. You can actually do it from first principles using the physical approach, because we did a few examples earlier, right? But the computer has no feel for any physical approach, it has to do it mechanically, blindly, and that too is possible. Before that, let me talk of this matrix K star, which is sometimes referred to as the unassembled stiffness matrix. Okay, let me give you a simple example. Let us take a truss. Let us say the truss has 4 elements. So I have F first element, there is only one because okay, 1 star, 2 star, let us take the first element F1 3 star. By now you know that the truss element has 4 degrees of freedom. We worked out the stiffness matrix in the last class, right? So this is F4 star, got it? This is related to D1 1 star, D1 2 star, D1 3 star, D1 4 star through a relationship which we are going to refer to as K1 star, right? This is the element stiffness matrix, it's 4 by 4, and you remember some rows are 0. Which are 0? Second and fourth. So because they refer to shear forces in a truss element, those shear forces are 0. So we know that these are anyway going to be 0, and so the columns also will be 0, right? And the non-zero values, what are they? They're very easy to remember. So the principal diagonal will have A by L of that element 1, yeah, minus comes to the off diagonal elements. Right? Now if I take the next one, which I'll put as F2 star, okay, I get another one like that, right, is equal to K2 star into D2 star. Does this make sense to you? Similarly, I get, let us say there are m elements, I can write these matrices, right? Now if I want to relate all of them to a single matrix, okay, so this is really meaning F1 star, F2 star, etc. This will be right? How will this look like? Let's say this is dimension m by 1, m members. This will be m by 1, right? And each of them will be 4 by 1. So the actual size will be 4m by 1, right? But let's look at the sub matrices and not worry about this. Okay, so we don't worry about this. What will be the size of this matrix? M by m. What will it? How will you make it? How will you arrange it? You've got all the individual element matrices. How will you arrange this?
Put all these next to each other.
No?
So K1, K2, K1 star, K2 star, diagonals.
Wonderful. See, the element stiffness matrix for one element has no relationship with the element stiffness matrix for the other element. So if you really want to put in a matrix form, there's only one way you can put it. This will be a diagonal matrix where you have, say, K1 star here, K2 star there, all the way here, and you have zeros everywhere else. Is it clear? Because then only I get this is equal to this times that, which is this. This is equal to this times that and nothing else. So this is sometimes referred to as the unassembled, because you've really not assembled the structure. You just put together the all the element fellows together, but it's not the structure stiffness matrix. So this is called the unassembled element stiffness matrix. Does it make sense? That's what's shown in the slide here. Okay, so it's always a diagonal matrix, and if you do the transformation here and see, it's a simple transformation. Okay, I need to explain this transformation. Okay, this depends on the contragradient principle, which I showed you, but I have not proved it. I'll prove it a little later. Let's accept this principle that the reverse works this way, and so you can prove that it takes the same form. This form is familiar to you because we did Ti transpose Ki Ti. So you have a similar transformation here. So you see, you get the same structure stiffness matrix from the displacement transformation matrix this manner. So let's say you get Td, let's say you got K star, you got K by this method, and if you don't want to do it for the whole structure, you want to do it element by element, that's also fine, but then you have to sum up for all the elements. I want you to understand that unlike the previous case where we dealt with Ki, which was always limited to the size, it's a square matrix, size 6 by 6, this K is a structure stiffness matrix size. It's as big as the global degrees of freedom. You will understand when we do an example. And then you can have these relationships. After you find the displacements, you can get the member end forces. So let me put it in a different way. If I want to generate the structure stiffness matrix using this approach, the displacement transformation matrix, first I create this relationship at the element level, putting all of them together, so it's unassembled. Is it clear? Exactly what I've shown on the board. Then in the real structure I know this is what I want. Okay, now my playground is different. Now my playground is, on one side the goalposts will have the structure level coordinates, on the other side I have all the element level coordinates put together in an unassembled manner, but all of them are there. Then my Td will take this path, right, because d star is Td into d. Okay, I have not partitioned dA dr, but you can do that. Is this clear? Let me ask you, is this step clear from here to there? Is this step clear from here to here? This is your conventional stiffness matrix. Is this step clear from here to here? Okay, that's how to get this Td is what we will see shortly, but once you have got Td, you have the same game going on. That will be Td transpose. We will prove that it is so right now you accept it as it is, and then you have this shortcut along the diagonal, and so you will get this. So this also establishes the same relationships. Let's see this problem which we did in the last class. I am just showing you to remind you that we did this using Ti. How do we do the same thing using Td? So let us see. Remember in Ti those were our non-zero elements. The transformation was very simple. You had a cos theta and a sin theta and a negative in one of those. Okay, let us look at the same problem, and here we are using the Td in the conventional stiffness method. What do you need to do? Well, I am not going to the global axis here, I am sticking to my original 1 star, 2 star, 3 star, 4 star, I am not doing any switch at this stage. Then I need to develop this matrix, right? It will look something like this. Okay. First of all, in this truss element I have 4 degrees of freedom. So do you understand di 1 star all the way to di 4 star? This is my Td matrix, and on the right side I put all the elements that are there in this, all the coordinates in the structure, global coordinates. There are 2 active coordinates and there are 8 restrained coordinates, right. So the size of my Td matrix for any element I, there are 4 elements, is 4 by 10. 4 by 10. In case, are you getting it? It is simple, it is 4 by 10. Now how do most of the elements are 0? Let us prove it. Now how do I fill up these columns? If I want to fill up this column, what should I apply? d1 equal to 1 and everything else 0. If I want to fill up this, what should I do? d2 equal to 1, everything 0. If you want to fill up this, d3 equal to 1, everything else 0, right. Now do not you agree this box will be the same as the box we got earlier, because it is the same transformation, cos theta sin theta minus sin theta cos theta, right, because we are aligning to the global axes, because the global axes are pointing x and horizontal x and vertical y. So I have taken a short form, I have said let Ci be cos theta I, because I need not write so many letters and my matrix looks smaller, and sin theta I write as Si. So do you agree this is so? But there is one more box of Ci, Si, where should that come? Well, it depends on which of the 4 elements you are dealing with, right. Let us take the first element. This set of Ci, Si minus Si, Ci will come somewhere here. Where will it come? Will it come here, or will it come here, will it come here, or will it come there? Well, check the coordinates. The element number 1 is linking 1, 2 and 3, 4. So this is 1, isn't it? This is 2, this is 3, this is 4, because that is what the global coordinates point to. So where will it come? It will come there for I equal to 1. So the top corner is common for all of them, because 1, 2 is common for all the 4 elements in this particular example. What about for I equal to 2, the second element, where will it go? Nice. Now you see, it's nice, you are just kicking around a football. What about I equal to 3? I equal to 4. That's it. That's it. So you've got 4 Td matrices for all the 4 elements. K star is very easy. What is it? It's the same, it's this one, right? You can play the game and you can actually work it out. It's very easy to do it. And find Td and Ki as we pointed out, generate this, sum it up, and you will get to exactly the same form, right? Sure. Yeah? No, sorry. That should be sine. That's the same box which is going. That minus should not have been there. agreed, it should be all, it is the same box, well pointed out, thank you. Good, students should have sharp eyes to catch errors, right. So let me sum up, because we are just showing the big framework, we are not solving any problems. What do you do in the stiffness method? Well, your first job is to make sure that the computer is able to deal with the same structure that you have in mind. So you have to join, you have to give information regarding the joint labels, the global axis coordinates, identify the active and the restraint degrees of freedom, put them at the end of the list, give them labels and identify the incidence, which is your start node, which is your end node, and give the element material and cross sectional properties. In fact, if you take any software, that is the first thing you need to do. You input it, and once you give the coordinates, it should draw that structure for you to see and confirm. You say yes, this is. In fact, in the big software packages, you not only see the line, you can do what is called an extrusion. So let us say you have given an eye section, you have to make sure that the eye points in the right way, I mean it does not get flipped over, all that you can see clearly. So sometimes we make errors in the input, but you should be able to see it using some Visual C++. I am not asking you to do any of that, but then this is the first step. Next step, what do you think is the next step after you have given the input? That comes much later. I mean, I am not saying what you have to give, you are right, you have to give the loads. What is going on inside? The moment you give this, it is not waiting for loads, it is trying to be ready to handle your loads. No? So by the time you key in the loads, it would have done its homework. What is the homework? It will generate the element properties, right. So we have done that, the element stiffness matrix, the transformation matrix, either you can do TI, software packages do only TI, but lesser humans will do TID because no, you are not comfortable putting those brackets and shoving them into box. So TD is a blind way, you are really covering all the global coordinates. So what if most of the elements of that TD matrix is 0? Okay, then you do the product, and so that you are able to generate the structure stiffness matrix, and there are two ways you can do it, and finally you find that it is KAA that you need to invert, because only that forms the matrix which will help you get the unknown dA. So you do not have to invert the whole K matrix. For example, the trust problem, only K1, only 1 and 2, those coordinates. So K is really small, and when you learn in the university, they teach only that Ka. So you do not see KR, you do not see KRA, you do not see KRR, so you do not get confused. Now you get confused, but then you are trying to see the big picture and trying to see what is really going on. You are trying to capture the complete displacement field, the complete force field, and you decide what you want to do. Next you put in the load data, okay, and this we will see later. You generate the fixed end force vector, you find the unknown displacements by using the inverted Ka matrix, compute the element level forces, compute the support reaction, you have got everything, and all this happens in a jiffy at the press of a button. But inside the black box, we are trying to see what is inside the black box and how is it working. So remember, we have got some idea of what the conventional stiffness method is. We are now going to look at the reduced element stiffness method, and we will also look at flexibility method in the next class, okay. But something is common to these, and I want you to understand. In the last class we talked of 3 element stiffness matrices. One was for a truss element, same as the one I showed on the board. Second was for a beam element, and but we said there is a problem with the rank of these matrices. What is the rank of the first matrix? 1. Okay. So the question is, can you find the inverse of the element stiffness matrix? Is it possible?
No.
So is there a flexibility matrix for the element stiffness matrix? Obviously, because it's singular, its rank is not full, so you can't invert it. Does it mean there is no element stiffness matrix? I mean no element flexibility matrix? Because we have studied that the flexibility matrix is the inverse of the stiffness matrix. but clearly inverse is not possible. So what's wrong or what's right? Why physically, why is it not possible? That's the answer to a different question. Why are you not able to find a flexibility matrix for these elements? The answer is actually ridiculously simple, but I want you to say it. And mathematically it turns out so. So your intuitive hunch is justified by mathematics. Now you don't have the intuitive hunch, you try to see the mathematics and give me the hunch behind it. Why can't you have a flex? Why can't you invert it? What's the reason? I'll give you a clue. I'll give you a clue.
So just because
The clue is, if you take the flexibility matrix, what does it tell you? If you give some forces, you can find the displacements, right? If I have a structure and I push it, the flexibility tells me how much that deflection is. Now here it will not be able to tell me what the displacements are. Why? You won't be able to. Because there is something when you look at those pictures which should make you nervous when you build such structures. Why are you not nervous? You should get nervous when you look at those elements. Support. See, they are just hanging, floating in the air. Yeah? How can you build structures like that? If you push them, they will just, this is not outer space, right? So you don't get any unique results. These are unstable structures the way we have drawn them, right? That is the simple reason they are unstable structures. You have rigid body movements, so you have independent displacement vectors, which is fine, but you do not have independent force components in the force vector. That is a simple answer, but there is more to it. So the rank of this is 1. What is the rank of the second one? 2. Is it not? 2. And what about this one? The plane frame element. 1 is for the truss. It's 3. Okay, why it's 3 you should figure out by now. You can multiply, they are all dependent, they are not independent. Okay, so here's a summary of it. The element stiffness matrix is singular, non-invertible. Physically this is associated with instability, inadequate restraints, rigid body movements. The components of Di are independent, but clearly the components of Fi star are linearly dependent. The number of independent force components is limited by the number of independent equations of static equilibrium. So take the truss element. Theoretically you have 4 forces, but only 1 equation of equilibrium, right? So that is why the rank is 1. That is why the rank is 1. So it makes a lot of sense. So I am using the notation Q for the conventional stiffness method, where Q is 4 for the truss, plane truss element, but it reduces to 1. So I put a Q tilde, that sign is called tilde. Q tilde is 2 for beam element, Q tilde is 3 for a plane frame element. Now I want you to fill in the blanks. What about a space truss element? 6 by 6 is what you get if you follow the conventional stiffness method, but if you want to, what is the rank of that matrix? 1 chocolate for web.
1 6
more than 6.
The plane truss 4 became 1. Space truss 6 will become wrong. 1. Argument is simple. Plane truss, what is the equation of equilibrium? 1, because I tilt it and put it in space, it's still 1. So you didn't get it, so it's beautiful. So who would manually ever dream of doing the conventional stiffness method to do a space truss when the reduced element stiffness method offers you such a drastic reduction in the quantum of work involved. So that is why it is good fun manually to study the reduced element stiffness method. So for a space truss it remains 1, for a grid element it is 3, for a space frame it is 6, okay, 12 becomes 6. So I bring a new notation here, okay, the tilde is my notation for telling you that this stiffness matrix, this element stiffness matrix is different from the stiffness matrix we talked about till now. This is dealing with the reduced size of the matrix. This has an inverse because the rank is full here. This has an inverse, and that inverse is called the flexibility matrix of the same size. So it is beautiful, that is why it is good to look at the reduced element and flexibility in one go, because the size of all the matrices are identical. Does it make sense? Okay, next. So let's look at this problem. We did this earlier, right? Now I have given 3 supports, okay, I can give any 3 independent supports. You see these things? I have actually made it simply supported. These 2 rigid links say that this joint cannot move. This rigid link says it can move horizontally, it is like a roller support, but it can't move vertically. Now this element is stable. If I apply loads on it, it will resist those loads. So that is the kind of element you are going to deal with from now on, and actually you should be more comfortable with these visually because they are familiar to you, and you know you can't play around with them, they are not mechanisms, they are good solid elements. But I have chosen simply supported, you can choose a cantilever also, you will get the same results, but we will choose it simply supported. Is it clear? Now how do I mark my degrees of freedom? Earlier I did 1, 2, 3, 4, 5, 6 for each. How do I do it now? How many do I get for each element?
There is 1 for the first element.
I have an actual degree of freedom because I am not assuming inextensible. If I assume inextensible, that goes. So that is my 1. Then I have 2 rotations. So 1 star, 2 star, 3 star. Much better than 1 star, 2 star, 3 star, 4 star, 5 star, 6 star, right? This is the reduction, it is a reduced element stiffness matrix we are dealing with. Is it clear? Would you like to do this or the other one? This when you are doing problems for yourself, that when you want to sell your software and make money. Okay, so let us proceed. So you have 1, 2, 3 everywhere, right? Does it make sense? Okay, these are my local coordinates. Now I can put it all together and I get my combined element stiffness. So for each of them it is like this, got it? That 6 became 3, that is all, much easier to handle, and there are 3 elements and I can put them all together, and that is my combined element stiffness matrix. Does it make sense? Everything that we did till now except the size is dramatically reduced, and you put a tilde to make sure that you are clear. So I have both, I have displacement vector, force vector combined, and when I put the relationship between them, it will be that diagonal unassembled stiffness matrix, or I put it the other way, I get it in this fashion. Now each of them at the element level will look like this, okay. The reduced element stiffness formulation has the advantage of enabling us to deal with transformation and stiffness matrices of small sizes. It is especially suitable when we wish to make simplifying assumptions in structural analysis, such as ignoring axial deformations in frame elements, right. However, it should be used with caution when dealing with sway type problems and those treacherous problems we have seen where the columns are sloping. There you have to use extra brain work, not worth it, might as well use a software way of doing it, okay. So you must use the right instrument for the right occasion. You don't use an elephant to drive a small nail, so, but we end up doing that. So let's look at the different types of reduced element stiffness matrices. Take this, it's a 1 by 1 matrix, right? Only 1 degree of freedom. What do you think the degree of freedom is? Well, I've shown this is simply supported, but I can pull it only in one direction. What is the displacement d1 star for this? Physically, what does it mean? It's just elongation. So that's easy for us. It's what we called EI earlier. Now we are comfortable. We are connecting with what we studied in structural. Structural analysis is actually very simple. And you have to, you should not lose that simplicity. So now we realize that, isn't it much better to deal with this than with that? But you have to deal with this when you are dealing with large problems. So you have to know both. Okay, that's your truss element, and we call that axial stiffness. What about your beam element? 2, you are familiar with this, the values will be 4 EI bell, 2 EI bell, right? What about the plane frame? 3, it's nothing but the truss element and the beam element put together, and we assume that the axial stiffness is independent. We ignore any axial flexure interaction. That's what we do in first order analysis. We will study later in the 7th module, there is an interaction because it behaves like a beam column. Right now we pretend there is no interaction. Not only we, all the software packages also happily pretend that there is no interaction, but actually you have something called a P delta effect, which we will see later. That is called second order analysis. Does it make sense? Okay. What about the flexibility matrix? That is very easy. I put it this way, I flip it over and I call this axial flexibility. And look at this, this makes sense. Remember, if I apply a moment here, what is the rotation I get there? L by 3 EI, and what do I get here? L by 6 EI with an opposite sign. That is what this matrix tells you. So it is not difficult, and by the way it is the inverse of the previous one, and similarly this works out. So if you want to put it all together, these are the 3 values for stiffnesses and these are the 3 values for flexibility. Very easy, and you have already learnt this, and manually you can do this, but you should also know the other one. How do I generate the components of this matrix for a plane truss element? I'll end with this definition. Okay, so let's take a truss element like that. How do I get the TD matrix for this truss element? Well, now I realize there is only 1 degree of freedom, though in my global structure I may have 1, 2, 3, 4. Now this 1, 2, 3, 4 I have shown for convenience. It may actually be 5, 6, 21, 22 in the actual structure. So those are happening there, but the elongation is given by how much these move. So this 1, 2, 3, 4 is arbitrary. Now basically I want to know if these joints move by some known amounts, how much elongation do I get? That is the meaning of this TDI. TDI is just how much elongation in the ith element, got it? So the elongation due to di1, actually this I can be removed, it can be just d1 because it is a global thing. How much is that? So you needn't put I here, okay? This I can be removed, but it is linked to the other I in the conventional stiffness method. Okay, what are these values? How do you work them out? Well, let us do it from first principle. You put d1 equal to 1, okay? How much will be the elongation? A component of that is cos theta. Will it be plus or minus the elongation? It will be minus. You put d2 equal to 1, it will be, can't you see the length of the element is reducing? It will be minus sine theta. If you take the other end and you pull it horizontally and you lift it up, right, That is your transformation matrix. Does it make sense? That is the answer to these question marks. We will stop here. Have you understood today's class? A little better understanding of yesterday's class, right? So you will find that with subsequent classes this knowledge will get solidified, but you have to do some reading on your own. Thank you.